We'll get started here. So go ahead and share my screen. Okay, so today we're going to talk about, well, welcome back from spring break. I hope everyone got a lot of rest and resets and had a lot of fun. So yeah, we'll get ready for our final push towards the end of the semester. And I guess a lot of you guys will be graduating, so exciting time for y'all. Today we're going to talk about error control coding, and then in particular linear block codes. Friday we'll talk about convolutional coding. Not sure if we'll get through everything today. This can be an entire course again, so we'll try to give you an introduction to these concepts, and so provide a nice baseline for you going forward. All right, so yeah, error control coding, we'll look at a channel model that we adopt for a lot of these cases. We'll talk about how we often packetize data when we transmit them, and how that applies here. And then we'll look at some definitions and go through the process of encoding and decoding, and then maybe we'll have time for an example. And we'll have a homework assignment associated with this that'll be due next week. I think that'll work out for you. It should be pretty straightforward. So all right, what do we mean when we talk about channel encoding and decoding? So as we looked at early in the course, this is our overall model. We're going to add redundancy in a structured way to be able to cope with errors from the channel. It's not perfect and introduces errors, which can either be distributed over time, kind of randomly, like as we note with additive white Gaussian noise, or it could be in a burst where you get a whole series of interference or fading or something like that, but you get a number of errors right in a row. And so we're using this channel encoder to kind of overcome that. And at the channel decoder, we're going to try to estimate the original bits that were sent from the redundant bits and the implied structure. So we add some redundancy and some structure here. We know about that structure, and we use that to try to do our best estimate of what the actual bits were sent. Two levels of doing this: we can detect that there's an error, and or we can, in some cases, actually correct that error. So but first let's look at a channel model. It's a statistical model of the channel. Is essential in creating an effective coding technique. One that is very common and usually kind of the baseline of these things is a binary symmetric channel, noted as BSC. Our inputs and outputs are in terms of bits, and so that would kind of look at not just a channel, but kind of the modulation, demodulation process and all the circuitry in between. So we're really looking at bits in, not symbols, but bits, right? And in and out. And that channel, for whatever reason, inaccuracies, noise, that type of thing, will change a 0 to a 1 or a 1 to a 0 with equal probability P. Hopefully P is small, but and it's independent of transmissions at any other time. So and that's what we mean by symmetric, in that the probability of changing a 0 to a 1 is the same as the probability of changing a 1 to a 0. And note that the channel is often not reciprocal. In other words, like a base station, cellular base station talking to a handset might have a lot more transmission power as opposed to the reverse, where we're going from a handset to a base station. And so, you need to analyze this in a particular direction, and cell phone terminology, we call that downlink or uplink. So a lot of times, most of the time, well, at least in my perspective, we form up the bits that we're sending in and subsequently the symbols that we're sending into packets. And that packet might have a header in it. So the first few bytes that are sent are going to have some meta information. There might be some symbols or bits in there to help the receiver be able to synchronize and know when the packet is starting, how long that packet is. In some cases, we're going to give you information on what the modulation is. So the header is usually sent in a very reliable, low probability of error modulation, like BPSK, or binary antipodal modulation. Whereas the rest of the packet might be sent in a more efficient manner, like 64 Comm, QAM, or something like that. So, if an uncorrectable error is found in the packet, using some of the techniques we'll talk about here, then the receiver, if it needs to reliably receive all this information, it'll ask the transmitter to resend it. So if you're doing like transferring the file where you got to make sure that that is all transmitted correctly, then the receiver will ask for the transmitter to resend that packet. And that's not always done. Sometimes you just drop the packet, and in a case of like video streaming or something like that, you don't have time to go back and ask for it again, so you just let a little glitch happen in your audio or video stream and just deal with it. But you don't want to actually assume that that packet is correct. You want to drop that packet. So now we have these concepts called bit error rate and symbol error rate, but also now a packet error rate. So some terms to take note of and remember. So we are going to introduce this concept called forward error correction, sometimes pronounced FEC. It uses codes to correct up to a certain number of errors in the packet. We can also take advantage of automatic repeat request, or ARQ, which resends a packet if it has not been acknowledged or acked by the receiver before some timeout. If you've studied TCP communications, that type of thing, these concepts are inherent in that, in terms of this ARQ and ACKs and that type of thing. Hybrid ARQ, or HARQ, combines both of these techniques. So it'll try to correct using FEC, but if it can't, it'll ask for the packet to be resent. And oftentimes that is done simply by a timeout, where the receiver will ACK every good packet received and not do anything if it has a bad packet, and then that'll eventually time out. So ARC and HARQ, these occur at higher layers of the network stack, so we don't talk much about them. All right, so error control coding. By transmitting extra bits, we can detect and sometimes correct errors at the receiver. So note here we have A bits in on the channel encoder and N bits out. And we're going to see that N is greater than K. So we have data bits coming in and encoded bits coming out. The structure in the code helps the decoder actually figure this out. When Shannon developed all his capacity theorems and stuff, where he said that if you have a certain amount of bandwidth and a certain amount of signal to noise ratio, you can achieve up to this upper bound of capacity. And basically, he proved that using random codes. But random codes are pretty hard for the receiver to figure out how to decode. So you can kind of randomize that coding process, but there's no structure in it, so the receiver doesn't know how to deal with it. But all right, so code rate is a very important concept, and it's a ratio of the number of input bits to the number of bits in our code word. So our code word is what's going to include all of these error control bits, these redundant bits. And so generally N, the length of the code word, is greater than K, the number of message bits, and it has to be, right? So we're adding redundant bits or additional bits beyond what is minimum to communicate the information. So so code rate's always going to be less than 1. And but here we're sending actually extra bits, so it's going to take longer to send our data, or we're going to need more bandwidth to send our data. But we we get a lot in return for that trade-off. So lower code rate takes more bits, and to a degree more symbols of time to communicate, but they're more powerful. So all right, distance is a very important parameter in these codes. You may have run into this in other courses in digital electronics and that type of thing, but maybe not at this level. So Hamming distance, Hamming was just another one of the guys that laid the foundation for all of this theory. And the Hamming distance D is an important measure of how effective the code will be at detecting and correcting errors. It measures the total number of differences between two code words by bit position. So in other words, this, assume you have a code word of 0101 and 1100. What's the Hamming distance between those? Well, if we look at this leftmost digit, there's a difference. So let's count that as 1. We look at the next digit, those are the same. So we don't count that. We look at the third digit, those are the same, so we don't count that. We look at the last digit, those are different, so we count that. So our distance is 2. We had 2 differences within that code word when we look at it bit by bit by bit. Okay, so a code has many code words and is characterized by the minimum Hamming distance between any pair of code words. So you might have 128 code words or something like that, right? And now we're going to want to know what is the minimum distance between each of those, the distance between each of those, and then pairwise, and then calculate the minimum. Yes, a question.
I was just going to ask, Professor, if you could explain the code word again.
A code word is the output of the channel encoder. So yeah, I didn't make that clear. So we have the message or the data bits coming in, that's K. The channel encoder transforms those K bits into N bits, where N is larger than K. And so the output is a code word. A particular code has a set of code words, and but they're not totally inclusive of all the available digital words, right? So we have K bits coming in and bits coming out, and is larger in K. All we need is a code word that corresponds to each of these K bits, right? So if we have a 2 bits message length, then we have 00, 01, 10, and 11. If we add a bit to that, then our code word might be 0, 0, 0, 0, 1, 1, 101, 110, or something like that, right? So those are the code words. You'll see that if you look at that, there's a few of those, available words, right? So if we have 2 bits coming in, that's 4 different words, right? If we have n bits coming out, and I said n is going to be 3, so we're going to add a single extra bit. There's 8 of those available to us, but we're only going to use 4 because we're only ever going to send a code word that corresponds to each of the bit combinations coming in. So that's basically how we can do our error control coding. Is if we receive a pattern of bits that is not a legitimate code word, then we can conclude that something went wrong, right? So so we'll see a little bit more about that later as we go along. So
another question. How did you find the go to the next slide more?
This slide?
Yeah, how do you find the Hamming distance? What is it? It's between the bits, but I don't know how you did it. If you just go over that.
Okay, so count up the number of bit positions that differ between these 2 words. Okay, so I just picked 2 as a random example: 0101 and 1100. Count the number of bit positions where there's a difference. Okay, so this first, the leftmost bit position is different. So we'll
First
count,
bits are different.
and the last one is different. So we'll count that one also. So the other 2, the ones in the middle, are the same between these bitwise. And so so our minimum, our Hamming distance between these are 2, is 2. Okay, so a code has many code words and it's characterized by the minimum Hamming distance between any pair of code words.
Seconds.
Oh,
For the error control coding.
I'm sorry, I cannot understand.
I'll relay the question.
For
Kevin,
the error control coding, how do you determine what extra bits are added?
did you get that, Professor?
Yeah, how do you determine what extra bits are added? Well, there's a whole family of different codes that you can choose from, and each of those codes uses a different set of equations to generate these redundant bits. Some codes are better than others, and for many decades, basically, if you're trying to get a PhD in this field, information theory or control coding, your dissertation was basically trying to come up with a better code than anyone else has done. And so we've gotten very, very, very sophisticated in the type of codes that our people come up with. Just coming up with a random code doesn't mean it's the best code, right? So that's where you try to take advantage of this structure. This field basically really came into its own via NASA, where they were sending these deep space probes out in the early 70s, the first ones that were going to other planets, and they needed to get data back. They had plenty of time, but they didn't have a whole lot of power on those satellites. And we're talking like 10 watts, and you're trying to go bazillions of miles to do that. So they would send like 60 bits in a code word for each bit of information that they're trying to get across. So very low, very low code rate codes, but able to extract this information over these incredible distances, where your signal to noise ratio is terrible, basically. So, all right, so the Hamming distance for a single code word is relative to the all zeros code word. Every code actually has a code word in it that's all zeros. So that Hamming distance relative to the all zeros is the number of ones in it, basically, right? Because if a code word has a zero in a particular position, it's going to match the all zeros code word. So we call that special Hamming distance the weight. So the weight of a code, particular code word, is just how many ones appear in it, when you look at the bit position. So, all right, a lower code rate tends to produce more distance, more Hamming distance between all these. We're adding more redundancy, and so the code is more sparse in terms of the legitimate code words versus the available code. All right, a minimum distance of 2 means we can detect any single bit error or any odd number of bit errors. But we cannot correct it. We need a larger distance from that. So let's think about that a little bit. If we have a minimum distance of 1, it means that each of our code words, or at least a pair of code words, only differs by 1 bit position. Well, if we have an error in that bit position, then it's going to look like another legitimate code word, and we won't be able to tell that there was an error. The way we're telling that there's an error is when we receive a word that is not a legitimate code word. And so if we have a minimum distance of 2, that means we have to change 2 bits in that code word before we get to another legitimate code word, right? So if only 1 bit is flipped, that's not going to be a legitimate code word. And so we can conclude that there was an error in that transmission. Okay. We won't necessarily know which bit was wrong, but we'll know that there was an error. Okay. All right, so if D is a minimum Hamming distance code, we can detect up to T bit errors if and only if our distance is greater than or equal to T plus 1. Okay, and we can correct up to T bit errors if and only if D is greater than or equal to 2 times T plus 1. So a little handy dandy relationship there. Finally, we can detect up to T sub D bit errors while correcting up to T sub C bit errors if and only if T is D, the distance, the minimum distance in a code is greater than T sub D, T sub C plus T sub 1 plus 1. So I don't have an example of this right away. Maybe we'll come up with that because this is an easy test question and stuff. So, I'll try to do an example for you later. With code words with a code rate of less than 1, we have more available bits to send the K bits of information from our data, our message data. Code words are the valid set of bits. If the received word is not a code word, then an error has occurred, right? So, all right, so now let's look at generating these code words, and then we'll look at decoding these code words, right? So let's get mathematical here. So we'll have a code word C, and it's going to be n elements long. Our message coming in is going to be k elements long. So we're going to packetize these things coming in, kind of like we do with mapping from bits to symbols in our modulation. And it's a little awkward that we're reusing some of the notation, but that's how the field is traditionally evolved. But here we're mapping bits to bits instead of mapping bits to symbols, but kind of a similar concept, right? So we're going to take k message bits and we're going to create a code word out of that. We're going to call G our generator matrix. A matrix is just another way of doing linear algebra, where we're going to have some things multiplied by each other and then some things added to each other, right? And so matrices are just nice ways of organizing these type of linear equations, right? So we'll create our code inside a matrix that we'll call G. G stands for generator. So now a note that all computations here are done in modulo 2 because they're all bitwise, right? So it doesn't make sense to carry one message bit to another or code word bit to another. Each bit is an individual bit of information. And so we're trying to encode these things on a bitwise basis. So we use modulo 2. And as a review, okay, so fancy talk, you can call this a Galois field of order 2. So if you do study error control coding much more deeply, you'll study this finite math algebra and that type of thing. But for our purposes, we'll just refer to this as modulo 2 and note that there's really no carry. What does that mean? So we're going to use this symbol for addition, a plus sign with a circle around it. And 0 plus 0 is 0. 1 plus 0 is the same as 0 plus 1 is equal to 1. And but 1 plus 1 is equal to 0, right? Because it really would be 1 0 if you were tracking that carry, but again, we're not going to carry, so it's just going to be 0. 1 plus 1 modulo 2 is 0. And multiplication is a little bit simpler. It's just anything times 0 is 0. Anything multiplied by itself, 1 times 1 is going to be 1. All right. So this matrix operation is linear transformation. Each code word is a specific linear combination of the message bits. Okay. The sum of any two code words is also a code word from linearity. And the all zeros code word is also a code word in any linear block code. So these are just some concepts. We're not going to prove these because we're trying to squeeze all this into 1 or maybe 1.5 lectures. So, but these are just some concepts to keep in mind. Now, we're going to define this thing we call systematic codes. And any linear block code can be transformed into an equivalent systematic form. What is that? Well, that's where in our code word, this whole box here, rectangle, is our code word. And our message bits come first, and then our parity bits. Really, what's unique about this or special about this, I would say, is that the message bits actually appear in the code. and then our parity bits are added to that. Sometimes we will interleave these or permeate. Can't talk today, and we'll reorder them, but this is anything can be transformed into this. And when I say transformed, it means using like those matrix row operations that you might have looked at in your first exposure to matrices, and how you can move rows around and do row operations by multiplying it by constant or something like that, right? So if we look at this, then G can be viewed as this concatenation of the identity matrix, which would produce your message bits, right? So we're going to multiply this G times the data vector coming in. So we want those message bits to come out the other side unchanged, right? So we do that with an identity matrix. And then we're going to concatenate the parity matrix on top of that. So the parity matrix is going to have a size of k bits coming in by n minus k, or the difference. Sometimes we'll call that a little m, lowercase m, the n minus k there. So, all right, so here's an example. This is the Hamming 743 code, and I'm going to ask you to work with this particular code in the homework assignment. And in fact, you'll see when you look at this presentation that some of the answers are right here on the slide. So, but what we're going to do is we're going to take this generator matrix. We're going to multiply the data vector by that G, and that's going to produce our C, our code word, our set of code words. Okay, so actually, it's not really a set of code words. It's going to be a particular code word, a number of bits that corresponds to this vector D. So C and D are typically vectors when we're actually operating with this, and G is a matrix. So again, we noted that G is kind of this identity matrix, K by K identity matrix concatenated with the parity matrix. We can multiply those through, and D times IK is just D, right? So, and then we'll have D times P. So that's going to be the portion of C that arises because of these parity bits. So we're going to denote that C sub P. So C sub P is a part of the code word that comes from the parity bits, all right? And so Hamming, for example, would be this. So you see here in green, that's a K dimensioned identity matrix, right? One's along the diagonal. When we say a 743 code, that means we have 4 input bits. Our code word is going to be 7, so the difference is 3. We're adding 3 parity bits, and then it turns out that this code has a minimum distance of 3. So this would be N, that's K, and that's D min. Okay, so we have here these parity checks. So we look at these kind of row wise as we're multiplying by D. So this parity for the code word would be multiplying D, the input D sub 1 times plus D sub 2. We're going to ignore D sub 3 and add D sub 4. Okay, so D1, D2, and D4. Modulo 2 added. The second parity bit would be D1 plus D3 plus D4. And the third one would be D2 plus D3 plus D4. Okay. And so we're just putting that into a matrix. And again, that's modulo 2 operated. So here's the set of messages and the code words that are associated with that. And you'll see that this is a systematic code, and that for each of these messages coming in, you will see that the first part of that is just replicated, right? 1010, 1010. The 101 is your parity bits. Okay, and so you can pick any one, 0011, 0011 with the parity bits 100. Now you'll see that there's 16 of these, but there's 2 to the 7th possibilities here, right? It's 128 different possibilities, but we're saying that only these 16 are valid code words. If we receive any code word that's not in this list, in this table, then we can conclude that an error occurred. And in fact, with this code, we can potentially correct some of those. All right, so that's how we generate it. Any questions so far? Okay, so now we're going to look at decoding these, and we're going to come up with some definitions here. Again, we're going to return back to the C sub P, and we're going to note that if we multiply D times P and then modulo add this C sub P, these two should be equal to each other, right? And so we're going to we can rewrite this as this type of equation, but it ultimately should equal 0, right? Because we're adding these things modulo 2 style, bit by bit. Okay, bit position by bit position, they're the same. So when you add 2 numbers that are the same, you're going to end up with 0 because of this modulo 2 addition process. Okay, so we rewrite this left-hand side in this matrix form, and so we have D times P plus C times identity matrix, dimensioned here by M, where M is N minus K, where that's a number of parity bits that we're adding, or a number of these redundant bits. Okay, so this is kind of our definition of systematic code. We've got D concatenated with CP, that's our code word. Okay, so I'm out of time on this Zoom session, so I'll catch you on the next one.
Okay.